Ready?
Yep.
Let's do it.
All right.
Cool. So I thought the framing, there's a reason we're covering stability and consistency today. This is therapy. It's therapy for you. It's therapy for us. A lot of inconsistency, a lot of instability. And I thought, well, what are the things that we can't control? What should we do on a Wednesday when the election would invariably not be decided despite all of our sleep deprivation and overcaffeination? And I thought, this is actually a useful distraction, but it's also important because it's a useful distinction. And so these are some things that we'll be covering today. It's also, we're in the week following Dia de los Muertos. And so you'll see our Dia de los Muertos skull showing up here a couple times. So we will also attempt to have fun, which I know is hard to pull off now. But I wanted to start with three challenges of tandems and traditional dyes. And maybe I'll start here, and I'll attempt to go a little bit slower on this than I have previously. And then that way, and you can maybe even pepper me with questions, because last time I stopped and it was like, oh no.
Yeah.
What have our tandem has been doing to us? And so let's spend some time doing that, and then we'll set up a ruler, if you will. We'll set some requirements for really the way that we think dyes should work, and then we'll show you how our NovaFluors perform up against that ruler, right? So hopefully some useful things in here when you think about your experiments and how to leverage new technology. But to focus this in just for a moment. And focus it on the published literature, we're going to talk about tandems and traditional dyes with respect to stability and variability. We'll talk quite a bit around consistency, and then later on we'll talk about dye to protein ratio, and then we'll also talk about compensation. But to focus first on tandem dyes and actually just their lack of stability in solution, here, I'm just showing some data here, from Joe Trotter and Holder Macon, and what they were looking at, Holder Maker, is examining intracellular staining in CD8 and CD4 T cells. And, and for a moment, we're going to set aside spectral performance, and we're going to just focus on the biology. And actually, that's going to be most of today. And you can see here that if you do this staining, what you can actually see, and so in this case, they've actually stained, using CD8 APC size 7 and CD4 PE size 7, is that you see dim, dim APC positive events here. In the population that's positive for APC size 7. And these are not true cytokine producing cells, right? These are not interferon gamma APC positive. And in fact, that because they're not incubated with a secretion inhibitor. And in fact, it's only dependent on the presence of this tandem conjugated antibody. And in fact, if you drop it off and you do a fluorescence -1, you don't have the CD8 APC size 7 in there at all, you get rid of these false positives. And make no mistake, these are false positives that are due to the degradation of this tandem dye. And it's not just APC size 7. You can see the very same thing with CD4 PE size 7, where you see these false positives, which is the breakdown of this PE size 7 conjugate. So you're seeing these IL-2 PE positive cells. But in fact, once again, these are not incubated with a secretion inhibitor. And it's only dependent on the presence of having that other dye, because in fact, you can drop those off, right? And so so this is, by the way, this is actually when you drop that CD4 PE size 7 off, and you can see that you get rid of those false positives. And so, really what this points to is, in fact, that you get these false positive events due to selective breakdown of the tandem dyes, right? And in fact, this is actually false positives associated with the use of these tandem dyes and their breakdown. And by the way, this breakdown is occurring in solution in an experiment. There's no special incubation times that are occurring here, right? This is just a standard intracellular experiment. And in the time of an experiment, you're getting the breakdown of these tandem dyes leading to false positives. What I thought was also particularly interesting was also that, in fact, this is a cell type specific breakdown. And this honestly kind of blew my mind. And so this is actually a paper that came out a while ago, in 2009. And so you'll have to excuse some of the resolution on the graphics here. But what they did is they looked at APC size 7 and APC H7, which were conjugated anti-CD45, and they looked at the degradation of this over time. And what we're looking at here is actually just 30 minutes. And so what they did is look at this decoupling. So very similar to what we were just looking at, the breakdown of a tandem into the single dye. And you can actually see, for instance, that both of these tandems break down pretty significantly, even after just 30 minutes, right, which is about the time of an experiment. But what I thought was more interesting about the findings here is actually that there was a cell type specific degradation mechanism here, right? And so, or I shouldn't say mechanism, but there was cell type specific degradation kinetics, right? And so if you look at, for instance, APC size 7 or APC H7, right, you get a good amount of degradation over time. And in fact, this seems to be much, there's a lot more degradation in some of these PMNs, right? And so pretty amazing, right? And then, very similarly, if you look at actually the scales here for a moment, we're getting up to 10%. God forbid you wanted to stay in monocytes because, after, 30 minutes, you've got 40% degradation. And that continues obviously out into an hour. And so pretty amazing the amount of decoupling that you're seeing and the fact that it's cell type specific, and honestly pretty scary. The other one, which is a piece of data that we're very fond of because this really enabled us to rethink what the stability of a label is some data from Paul Wallace, who's at Roswell Park Cancer Institute, which just wrote a small little blog post about this. And again, we're using the same ruler of, let's look at the breakdown of the APC size 7 into APC, right? And in fact, what you see is that if you fix cells in 2% paraformaldehyde, leave them in the fridge in the dark, you get a pretty large degradation just after 72 hours, right? And so you're getting that degradation of APC size 7 into APC. What I find equally as interesting is that if you give them no fixative after 72 hours, again, what we would expect based on some of the previous results is that you just at steady state get degradation of that tandem on staining cells, right? And so I guess three big points to make here. One is tandems break down with essentially no inciting from any type of solution that they're sitting in. Two, they actually do it in a cell type specific manner, which to me is honestly pretty terrifying from a biology perspective, because you could actually imagine that there being different false positives on different cell populations leading you down a pretty bad path. And that seems to be accelerated in many ways by leaving in fixative, which is really what we would expect. Okay, so if that wasn't scary enough, let's also talk around consistency. So in this case, I'll share some data from a customer of ours, Trish Rogers. And she did some really interesting work when she was looking at classifying fluorophores in this very large sorting experiment that she was running. So it was a 28 color sorting experiment she was running over a period of 6 months in autoimmunity with the end goal of performing quite a bit of single cell transcriptomics on the back end of these sorts. And what she looked at is in this case, this is essentially the sorting that you would expect. The signals that you would expect, but this is PD1-PE, and this is what you would expect from a very consistent antibody. And again, it should be, right? PE on its own should be incredibly stable in solution. This is across 3 vials of antibody from 3 different lots. It's still very, very stable. And in fact, the only shift you see here is when the fiber bundle in the instrument is replaced, so as predicted. So again, for a traditional dye, very good consistency here. Now contrast that for a moment with the variability now of a tandem dye. So this is APC size 7. Again, you can actually see here that this is a new vial of antibody opened on exactly the same lot, and yet on an incredibly consistent instrument, you have a signal shift, right? You get quite a bit of variability despite that. You see the predicted fiber bundle, but you have a large amount of variability actually in the positive signal for this APC size 7 across both lots and even among the same manufacturer, right? And so pretty amazing, right? And of course, we've also dealt with a couple of years ago part of these antibody lots being part of this BD Biosciences reagent recall. And if that wasn't enough, we also have to deal with the headaches in tandems of compensation. And we'll talk about some of the why on that. But I mean, really what this breaks down to is when you conjugate a tandem dye to an antibody, you're changing its fluorescence characteristics. And so what does that lead to? Well, it leads to a number of other headaches. And I think that honestly, while we accept some of the rules that we'll go through now, we shouldn't, right? And we also shouldn't accept the fact that we have to do and look at the consistency and the stability of these dyes as researchers. We should really think about this as questions we should be asking our manufacturer. And again, we'll do that in a moment. And I thought this was just amazing. This is some work from University of Iowa, who's just advising their users. It's important to use exactly the same tandem conjugate for compensation tubes. We're all aware of that, but I thought this really nails it down, right? You can't use tandems from different vendors, even if it's on the same antibody conjugate. You certainly can't use, and I think we know this, you certainly can't use the same tandem on different specificities, even if it's from the same manufacturer. But let's look at this one. This should be a little bit terrifying. You can't use different lots of the same specificity with the exact same tandem. Well, that's interesting. That speaks to something different, doesn't it, in terms of manufacturing and the way that these are being conjugated? Certainly, you shouldn't be compensating ones that have been formaldehyde fixed with those that aren't. Okay, also quite interesting in terms of the stability of these things. And then I thought the other one, perhaps maybe the worst of all, is that, the one that you've just purchased versus the lot that's exactly the same, that's 1 month old, you don't trust that either. And I think you'd appreciate that's also pretty crazy, right? That 30 days of exactly the same vial should be completely different from a compensation point of view. Okay, so now that we're adequately scared, I still wanted to say, look, like, tandems have their use. It gives us access to more wavelengths. It's not fret that is the problem, right? Fret is beautiful. Fret gives us the ability to transfer energy and get access to more wavelength, right? And in fact, this is what's led to this tandem dye explosion, right? Where we're able to access out further into the red across a number of different laser lines because of this tandem dye technology, right? And also, frankly, it's just easier to do this, right? You can slap another molecule onto a donor, and you can get that fret going. Now, that being said, the report card for these labels was not very good, right? I think if you brought a report card like this home, when you were a kid, you would definitely be in trouble, right? And so for tandem dyes, they break down, they lead to false positive events. They certainly break down a fixative solution, right? They exhibit day-to-day, vial to vial, and lot-to-lot variability. They're also a pain to compensate, mostly for all the reasons above. Traditional dyes, another thing that we'll bring up in a moment, is they must be conjugated to antibodies at a molar excess, right? So you actually have to throw an excess of dyes. We'll describe that later on. And because of that, they actually have a Poisson distribution of the dyes on the protein. So something that we'll discuss in a moment. We haven't even talked about cross-excitation and spread yet. We actually haven't mentioned on any of the spectral performance of these things yet. So with that being said, and with a focus purely on those items and taking a look at that report card, if you will, and trying to invert that into requirements, we'll talk about the stability of our NovaFluors, and I mean really, truly stable. We'll talk about Poisson control, right? We'll talk about what that means in terms of labeling, what that means in terms of consistency, and then we'll talk about compensation, and we'll talk a little bit about applications, right? As a reminder that we've built these requirements on top of the requirements that we make for fluorescence. And so I'm not going to speak too much about this today, but we specifically engineer our labels, of which we have 17 unique colors across 19 labels on the blue, the yellow, green, and the red laser, to be uniquely excited by one laser, so to not exhibit the cross laser excitation that you see with other traditional dyes, and also emit cleanly. They're also incredibly consistent. This is something that we'll discuss today. Actually, what you're seeing here is actually just labels that have been left in fixative, and they're spectrally stable, so I'll discuss that a bit more in a moment. And we also have the ability to tune brightness on this platform to actually tune it to antigen density. So we're not going to actually dwell on number 1 or number 3 at all today. We're going to purely focus on the practical aspects and discuss stability and consistency. The way that we're able to do anything that I just described, whether it be the items around stability and consistency or be the items around spectral performance, and thinking about designing labels that are both uniquely excited off a laser line and then emit, if you will, into a small band, is that we bind small organic dyes onto oligonucleotides. We can assemble them into this Phiton structure, this incredibly stable and rigid structure that enables us a platform on which we can choose different dye components and also leverage fret. So again, while we're leveraging fret, which is great, these are not tandem dyes, as we'll describe. This talk could also be called "These Are So Not Tandem Dyes," and prove that to you through the use of data, both on the stability side. We've got other talks that cover some of this, but all of the spectral items for this as well. But what this also enables us to do in terms of, we can tune the excitation, the emission, we can tune the brightness, because we actually have 4 different independent arms of this Phiton structure. And then it's also very flexible in the sense that I can actually hang an oligonucleotide off at the end of this structure and use that to conjugate it to antibodies. It's also worth saying that this structure, because of these crossover regions, is incredibly rigid, right? Which means that if you will, the fret is fixed, right? That when I say that there's a label that it is excited at a certain laser line and emits at another, there are no changes upon conjugation. It's incredibly stable in that regard, right? And we'll see just how far we can push that today. So, I think one of the things you could say is, well, what questions should I be asking my vendor? How can I take this conversation that we've had around stability, around lot-to-lot, and turn it around and make that a requirement for what I should purchase? And I'd say, Seddon in particular, who's been building our, built a 40 color panel and is actually very actively, and by very actively, I mean like right now, finalizing this and running a 45 color panel. We've been through the ringer on this in terms of what we should be asking vendors on as we build up a large menu of antibodies just internally for the work that we're doing. And the questions that really we should be asking, because we don't want to take this work on ourselves, because heck, we're purchasing a product, is, well, what is the shelf life stability? Have you tested room temperature stability? What's the fixative stability? What fixatives have you tested? Are there spectral changes upon fixative? Also, can you share lot to lot data for your conjugated antibodies and your fluorophore? And do you see any vial to vial variability? And so, I figure we should be asking these questions. And so if, what's fair is fair. So we'll ask us this. And then hopefully you can use this, if you will, as a checklist to go ask, your other vendors and say, I'd really like to know, right? What does that look like? And so again, we also posted something up on our blog that just describes and has this posted in terms of like, here's the checklist, for you to use. So let's cover those one at a time, and we'll focus first on stability. And so, we've pushed this very hard, and so I'll describe a set of experiments here, and I'll do it for both the fluorophores as well as the conjugated antibodies, because we do offer conjugated antibodies, and again, something we'll describe in a moment. But under 2 month storage, just for the Phiton labels. And in fact, what we did is we just created a set of our first 6 blue and yellow green labels, and just quite literally left them in the fridge. No special solutions. They don't aggregate. They don't require special solutions, to be used together. And then 2 months later, conjugated them to CD4-SK3. And what we saw is, in fact, that they have exactly the same performance as they do as fresh labels. So there is no degradation of the fluorophores. We don't see any loss of performance just when we have just those Phiton labels in solution for both the Nova Blue and for these Nova Yellow labels. The other thing, though, too, if you remember, we were talking about the tandem dye degradation occurring essentially within 30 minutes to up to an hour, or some of the other data around 72 hours. What we also looked at was 2 weeks at just room temperature, right? And what would that look like? And again, this is actually just the Phiton label. We're not getting into conjugated antibodies yet. And in fact, this label, and as I mentioned, is so incredibly stable that in fact, if you pull it at day 7 and day 14, there's actually no change anywhere in the spectrum of these labels, even if you just leave them on a bench. So you'll see in a moment where we push that a little bit harder on the conjugated antibody side. The other thing too is we looked at fixative stability, right? And this is actually on the conjugated antibodies, and this is the bar that we set earlier, again, where we got these tandem dyes breaking down after 72 hours. And what we did is actually stain with anti-CD3 that was conjugated with our Nova Yellow 610 dye, and then left them in fixative. We did not fix them and then resuspend them in PBS. We literally left it in 2% paraformaldehyde, and then we came back and compared that to cells that were freshly stained with exactly the same conjugate. So here's just showing fresh. We can stain T cells, so there's no magic there. But what is really impressive is that these conjugated antibodies in these labels have exactly the same fluorescence as they do versus fresh, right? So in fact, there's no difference. So this takes care of a lot of those items we discussed around both the pain of compensation, but also just shows you that they are incredibly stable in solution, both in a label form and also in a conjugated antibody form. And so we've been showing this result for a couple months now, and people thought, wow, that's really interesting. So they asked a question, which is it spectrally stable? In other words, are there any changes anywhere else in the spectrum? And so what I've done here is actually just blow this out across all the detectors that we have. It's just run on an attune. You can actually see that there's actually no change anywhere in the spectrum either. So not only are they very stable and fixative, and they don't break down anywhere, we just haven't seen it yet, right, out to 2 weeks. So much more stable than the tandems, but they're also spectrally stable, right? So I think this is exciting when we think around what the limited capacity in labs are, or sometimes having limited access to a flow cytometer. The ability to fix these samples and have them be spectrally stable, I think is honestly, hopefully, as exciting to you as it is to us. The other one too that I said I was going to push on a little bit harder, I showed you the room temperature stability of just the fluorescence labels a moment ago, but it's also what can we do with respect to conjugated antibodies? And so, everyone has their own favorite name for this experiment internally. It has been called alternatively the lazy graduate student experiment, the Europe shipping experiment, or the Australian shipping experiment. Regardless of what its name is, it is essentially what we did is the simplest experiment ever, right? Is we took conjugated antibodies and either left them in the fridge or left them inside of a lab bench. And that's it. Not inside special buffers, nothing else, right? They were just inside of PBS. And then we stain cells after 2 weeks of storage under either of those conditions. And in fact, what you see here is that there's no change if you leave these at room temperature, right? So there's no change in the staining. And so these are incredibly stable. And so again, we've shown this for about a month or two now. And so we wanted to say, okay, well, what does this really mean under the covers, right? Like, what does this look like when you really dive into the details? And let's really stack it up hard against what we've seen with respect to tandem dyes, which have an incredible amount of breakdown. So what I'm showing you here is actually just the median fluorescence intensity versus time across these 2 weeks for all of these conjugates. And you can see that they are bang on consistent across all of these days. So we don't see any changes with respect to the MFIs. Again, if you're running this on a stable instrument, you shouldn't expect to see any changes. The other thing we wanted to look at though too was, is there any increase in background? So right, not just the median fluorescence intensity, but we actually looked at the separation indices of these labels as well. And so what we're looking at here is accommodating for the median of the positive minus the median of the negative, but also taking a look at the 84th percentile of the negative. Because imagine a case where you still have the same median fluorescence intensity, right? And it's great after 2 weeks. However, the background, for whatever reason, has been increased, right? And so that's why, for instance, this, what we're looking at here, if we've got something that's in this green here, we should really be dinged for that. There should be less separation because we're getting less separation in between the positive and the negative populations. And so if you look at these separation indices across these days, out from measured at 4, 7, 10, 7, 11, 14 days, you can see there's no change in the separation indices. So we're not affecting the background either. So they're, again, incredibly stable through this view. And the final part of this would be, well, what does it look like spectrally, right? Is there any change after 2 weeks when you just have left these on a bench again? And is there any change anywhere in the spectrum? And so I'll flick through this one color at a time, but the answer is no. There's no change anywhere in the spectrum when we take a look at this after 2 weeks. And so I thought, really honestly, some incredible performance from these conjugated antibodies, and gives us the ability now to have a lot of confidence in what we're seeing. Seth, is there a question?
Yeah, there is. The question is, could you please throw some light on tandem/FRET dyes for SARS antibody conjugation? And then the second question, I'm not as clear on, are NovaFluors into FRET series? I think maybe, are they working through FRET? Maybe is what the question is.
Yeah. So let me tackle the second one first. So the answer is yes. So there is FRET occurring on the Phiton platform. The difference being that, as I've shown you, because they're attached to a DNA platform, not to one another, and the geometry is fixed, you don't see the differences that you see with tandem dyes when they're conjugated, and then all the other characteristics that I showed you. Right. And so the other thing too, as a reminder, right, is that FRET scales with the square of distance. So we can actually use that platform also to tune, if you will, we can choose different components, and then we can also change the geometry of the FRET, right, to get characteristics that we want for a particular label. Right. So the answer is yes, we are leveraging FRET on the platform, but doing it in a very different way than what you're seeing in a tandem dye. So I think that's probably pretty clear, and hopefully that answers your question. On the SARS-CoV antibody front and use of tandems there, I think when I think around the work that's being done now with respect to like NovaFluors in that type of work, I am not sure if anyone's using it on the spike, on anti-spike antibodies currently. It's hard to tell. So we offer, as we'll discuss in a moment, we offer conjugation kits, CD4 kits, and then also conjugation and conjugated antibodies. We are not currently offering an anti-spike protein that's conjugated to NovaFluors, but that doesn't mean that someone hasn't done it with the conjugation kits. It's a good question. I think the work that we know is occurring is there are quite a few folks who are looking at chemokine receptor expression or other antigens leveraging NovaFluors and leveraging the clean fluorescence aspects for just to have high faith, essentially, that you don't have any contribution from spectral spreading. And maybe one more point, which is that the fixative stability that we've got of these labels is really attractive to people who are working in human samples, because they can fix those samples, right? And if there's even a suspicion, for instance, that there's an infectious agent in there, they know that that's not going to cause a large degradation in their tandem. So hopefully I've answered your question. Again, we try to keep in touch with as many customers as we can, but it's sometimes it's hard to track, what all is occurring, particularly with conjugation kits. Okay.
All right.
Cool. So hopefully, yeah, it seems like those are great questions. Hopefully I've covered some of the stability aspects and how we're quite a bit different there. I think the other thing too is a reminder, if you will, is on the consistency front. And, this is one that I think, both Seth and I were definitely scratching our heads around as we ordered more antibodies and saw lots of differences. And, we thought, well, what's behind this? And, it turns out that what's behind that is and you can see this question is important, is lots of data for both conjugated antibodies and fluorophores, right? Because honestly, antibody manufacturing is pretty easy, right? Like a lot of antibody should be a lot of antibody. So, you know, it leads you to this point where you realize that the variability that you're seeing lots a lot is down to your fluorophores. And so how do we make that a thing of the past? And so we've been very open with our lot-to-lot data, right? And so these are actually two different manufacturing batches of our 6 labels, again, off the blue and yellow green laser. And so what you're seeing is what you're not seeing here, right? In fact, these look like overlays because they're incredibly consistent across the entire spectrum. And in fact, I'll take that one step further, which is that if any label is more than 5% different, right, which is the variability of our measurement instruments, anywhere in the spectrum, we'll toss it out, right? And so that what we're showing is incredible consistency across the spectrum for the labels themselves. But we want to take this again and one step further. And so what we did is we took both lots and conjugated them to CD4 and then sent those out to an outside lab that's got an incredibly consistent instrument and said, test these, right? Compare these to an old lot that we've sent you, a month ago and see how they perform, right? And so this was run at NIAID, in this case, looking at the NovaFluor dyes. And what they did is ran a titration on that conjugated CD4, again, for both different lots and compared them. And what we see is there's actually no statistically significant difference in the separation indices with these different manufacturing lots. Applies for the NovaFluor and it applies for the NovaBlue. So I'd encourage you to ask your vendor, can you show me the lot-to-lot data with respect to your fluorophores? Can you show me the lot-to-lot data with respect to the conjugated antibodies? And particularly when it comes to the polymer dyes, this is a huge issue and it's something that we've been dealing with, again, as we've been working through these larger panels. So hopefully that checklist is equally as interesting for you. Another part of this that I'll be honest, when we gave a seminar a year ago in DC in person, which is sort of kind of blows my mind now. We talked about this concept of Poisson labeling of an antibody, and honestly, even though I had been in the field for a good amount of time, it was still a shock to me when I learned this and really started digging into this. And so, people, when I presented the first time, they encouraged me to say, okay, hold on, can you replay that part again? And so here's the concept. So in fact, and let's start with this quote up here. If you go to an antibody vendor website, what you will see is that the typical fluorophore to protein ratio is 3 to 7 to 1, right? Now, what that means is that there is an enormous amount of variability with respect to the number of fluorophores dyes that you're getting on the antibody. And in fact, you can see here that it's really unknown where the preponderance of that is. Now, it's likely, just because the way that this works, the way the physics work, is that there is a Poisson distribution of those fluorophores on that protein, right? Not for something like PE, which is enormous, and so it includes the binding of other fluorophores, but for a number of other labels, that's what you're dealing with. It's a huge distribution in the number of labels that you're getting on an antibody. And so consider for a moment that even before you get onto the flow cytometer, you're introducing a pretty large amount of variability and fundamentally hamstringing your ability to use these in a quantitative fashion. Because how are you supposed to know that it's not just the degree of labeling, it's just the number of fluorophores on a protein? The other effect of this is what I'm showing here on the left, which has a number of honestly pretty pernicious effects, is that to make these antibodies, you've got to add excess fluorophore at either 5 to 1 or 10 to 1. It's obviously a big cost driver. The second thing is that unreacted fluorophore must be removed. And in fact, if you're leveraging other customs programs, there's the opportunity for having free dye in solution, right? Which can of course bind onto cells. And it still results in the spread of DOL. If you think about it, right, you've got just an excess here. So the stoichiometry means you get this Poisson distribution of labels. And we thought, well, wow, that's particularly when it comes down to, what we're attempting to do with respect to consistency and stability. What we really want to do is say, okay, can we move beyond this? And can we shift this to a point where we are getting something that's 1-to-1 labeling? Because then you could move flow into a much more stable and much more quantitative system. And so what we've done is developed a 1-to-1 conjugation system in which we have a known, as I've shared when we were talking about, Fret during that question in a moment, just a couple moments ago, where we know we have a controlled number of dyes on the Phiton platform. We know exactly how that should behave every single time. And what we're able to do is just get one of those Phitons on one of those antibodies. And in fact, one of the things that's really, really interesting about this is that it moves us away from this 3 to 7 world and into a 1-to-1 world. We have a precise degree of labeling. And in fact, the conjugated antibodies that we offer now, and also our antibody printing system, which I'll describe in a moment, all leverages this technology. So we know there's one Phiton on one antibody, right? So if you contrast this where you've got the, the labels per antibodies and number of antibodies in this degree of labeling, this fluorophore to protein ratio has a Poisson distribution, we have a highly controlled number of dyes, right? And in fact, it is 1-to-1. And so we've got a number of different folks now who are looking at using this to quantify. And so perhaps getting back to your question around the spike protein, I think this becomes very, very interesting when you think around whether it be, spike or whether it be, versus viral receptors. If you're wanting to go in and do some quantification, I think this is a pretty interesting tool to consider, right? Is how could I leverage this notion of 1-to-1 labeling to begin getting in there? And if I run a standard curve, go in there and think around actually quantifying the number of receptors that are on a cell. So the final part of this is actually kind of the easiest one in a way, which is hassle-free compensation and applications. And really, with respect to compensation, which is it's pretty easy, that frankly they don't break down. There is a rigid DNA backbone. They're spectrally and chemically stable, which we showed 5% variability. And this notion of easy to compensate is it is what it is, right? There are no changes upon conjugation of these antibodies, and so you can leverage CD4 or some high antigen density marker and use them for compensation. I've shown you this notion actually of no molar excess needed in precise DOL. We're actually working on a larger data packet for that now, but everything actually that we already offer is already 1-to-1 labeling. And so again, this is actually perhaps our shortest webinar, but hopefully some interesting points to consider for stability, what we're doing with respect to moving beyond Poisson labeling, hassle-free compensation. And I don't have my standard sales slides in here. I just figured, we've been sold enough over the past several hours or several months, if that's the case. But just to describe this for a moment, our catalog is up here. I've also put my email address up here. So we offer a set of things to get your hands on these labels. So we offer a conjugation kit, right? Either for the first 6 BYG label, which we essentially sell as a 6-pack, which is a 6x100 microgram kit. We also offer the individual colors as 1x100 microgram kits. We also offer a CD4 kit, which is great for the characterization of these labels across a number of different instruments. And then, as I mentioned, we do have conjugated antibodies now. So if you go on our website, you'll see that we've got a set of 12 different specificities. But what's, I guess, equally as interesting there is that actually just last week, we sort of launched this ability to actually print antibodies. So we can actually hold any of our colors that we have in stock across any specificity that we either have and actually print those out in a 1-to-1 format, do those for both antibodies that we have in stock, but then also do them for any customs program. So we've done this for a number of different government institutes, and now biopharma, we actually are printing their antibodies for them at 1-to-1. So again, concise webinar, but hopefully interesting to you, and we'd be happy to hang out for any questions.
Yeah, thanks for presenting all that, Mike. So one question I guess I've always had, and I don't know if other people have it, is why exactly is like size 7 specifically? Any thoughts on sort of why that is so sort of fragile, in terms of these fixatives, or is there something about that chemistry?
Yeah, it's a good question. I was thinking about, what that chemical linkage is, and I think it is down to the susceptibility of that linkage to those fixative solutions. It's a good question though, because think about something like, I'm not a chemist, but I believe it might even be the sulfonation of some of those side dyes because they're sulfonated by default, that's leading to that degradation. But don't quote me on that. I am not an organic chemist. But I'd say too, it's interesting in the sense that you also see this for H7, right? And so you certainly do see it broadly for APC size 7, for PE size 7. I'd say too, I don't think that there's been extensive work on all of the tandems. Right. So, for instance, how do the fire dyes perform in this regard? How do other dyes perform? And and what's the chemistry? Is there essentially like a level of susceptibility to all of this in terms of the fixative stability and then also the cell type stability? I think at the end of the day, when I think about it from a practical perspective, I mean, you're still dealing with a one chemical moiety, attachment, right? And so you're still going to have some susceptibility there because you're not putting them down onto a rigid scaffold. And the other thing too is, regardless of all of that, that every single time you do this for any tandem, when you conjugate it to an antibody, you're changing its fluorescence characteristics, right? And so to me, that's kind of scary, because regardless of the chemistry for a moment, it means that all of those lot issues, fixative versus non, 1 month, all of those issues still apply, right? And so for me, I think when we think about this, when we're running our own experiments, right, it's like, I think the the lift that we have is like, look, you can go to the fridge, you get that antibody. It could be now, it could be 3 months ago. It could have been stored. I mean, shit, it could have been left on the bench. And it's going to be exactly what you expect, right? And I think that thinking about how that moves us beyond some of these tandem dye issues, I think is important.
All right, so we've got a question from Svetlana. So she was excited about the webinar, but she said that the spectral stability assessment on Attune seems to be an overestimate. So have we done spectral stability assessment on the 5-laser Aurora or Sony 700 XL, which really covers the full spectrum?
Yeah, we need to do that. So absolutely, it's spot on. So the goal here was like, how close can we get on the Attune? Because we certainly need to run it on the Aurora, which we're using a little bit more for some of these higher parameter experiments. But yeah, we certainly have to run that. And then I like the idea though, which you put in there. So we've just got our first really 2 customers with access to an IDE 7000. And I think that when we look at an Aurora, the idea, they're great instruments for doing this kind of work, right? And so I think that'll be what will be the next exciting part of this. And so we'll certainly be able to test some of the CD4 conjugates with room temperature across those, because now we've got customers that have access to those. And so, yeah, point taken, we've got to run it that way. But I think for us, encouraging that it's as stable as it is across the spectrum.
So here's a thought experiment I think is kind of interesting, that, if you were, if size wasn't a constraint and you were dealing with somewhat like literally setting up the same tandems, but putting that on the Phiton, do you think, that would behave better if that was, if the size wasn't obviously an issue for a lot of the tandems that you directly compare?
Yeah, and if you think about it, size is only an issue in the sense that if you think about you just think about the way that these tandems are set up. You could also, you could create a larger structure in any, essentially a larger Phiton structure, right? Because if you compare something like PE, which is 240 kilodaltons, that's almost, it's 100 kilodaltons more than the actual Phiton structure itself, right? Which is 150. But you could certainly create a larger scaffolding structure to get these tandems going. I think you could certainly control the geometry a lot better and control that consistency. The question would be, how do these enormous structures lay down, and what's the photon efficiency of transfer? What's the transfer efficiency in between these different moieties? Or is it sort of like a cheap way of getting the fret, is just putting them as close as possible to it? I don't know, and I haven't seen anybody. I mean, the fret scales of the square distance, but it's hard to think about, like, okay, would you titrate out the length? Mm-hmm. Right, for these different size fluorophores, right? I don't know. And then would you see what would you see? Would there be like a exponential decay in the fret? Or again, we don't know.
Yeah, I just figured it was an interesting thought experiment since we're talking about tandems. I think that it's interesting because the Phiton can also act as that solubility cage. So I think there's certain ways in which, even for something that was perhaps less stable, and of course there's not a good way to test with something that large as a comparator, but I suspect that would also help with stability. So
I think the bigger point to be made there is that you can use dyes that have never been used in any fret, or just dyes that we're not using in flow, right? And leverage the platform capability of the solubilization, as well as some of the ability to fret them. Because it's interesting. It is interesting when you start on the dye development side, when you start seeing how these things perform, they'll perform quite a bit different when you can put them in a very controlled fixed geometry, right? And that to me that's been a big surprise. So it's expanded our menu of things that we can create and leverage on the platform.
Yeah. So I guess in terms of as we're looking at sort of different tandems and sort of as these comparators, how are we controlling, I guess, no, that's not a good question. Sorry. So sort of thinking out loud, that's just a problem. But I was just trying to think about sort of, the controls on the chemistry versus what is happening, sort of in these other tandems. So it's more, again, speculation, but just, I think what this sort of idea opens up is a lot of ideas about kind of what is actually happening with your chemistry. What do we not know? So
yeah, and it's, it becomes a question of like, do you create a catalog of all the tandem chemistries, or do you just focus in on the items that you know that you can, where you can essentially beat the tandems, right? And, you know, for us, it's been that focus. I think the other thing too about your point around size that's worth bringing up just from an applications perspective is what you've seen with FOXP3, right? Where we have, there's just interesting results there where it, you know, it seems like, you know, the FOXP3 that's conjugated to a NovaFluor, because it is smaller, the NovaFluor is the same size as an IgG, seems to honestly be both brighter than and have access to more of the FOXP3 species. So you actually get higher staining. So you actually resolve FOXP3 low and FOXP3 high populations, right? An experiment that we're repeating now, but I do think that there's another concept in here, which is that the size of these tandems is quite large, right? Particularly when you think around a PE tandem, you know, you're leveraging that on a 240 kilodalton backbone. Then you've got another, again, a small molecule dye that you might be attaching to that, but these, you know, these can be quite large. Right. Cool. All right, well, I'm going to go back to being anxious about election results. And so I appreciate everyone showing up today, and we'll hang out maybe for another 2 or 3 minutes if there's any further questions, but appreciate you guys showing up today.
Yeah, thanks so much. So you got a comment from George. Size does not matter as long as the product works. It all depends on your application, of course, but yeah.
George. Oh man, you always getting me. Agree. Agree. Oh man, so funny. Awesome. Cool. All right, I'm gonna end this with that. That's a perfect mic drop from George Mac. Just boom. George dropped the mic. I love it. All right. See you guys.